Well, so we'll start a new topic today, which is gravity. And we have talked all along that there's a force of gravity which acts downward on a mass m, and this force of gravity is given as mg. Now, what is the origin of this? Well, Newton tried to explain this in the year 1600, in the 17th century, and he said that this is because if we have two massive bodies, let's say one has mass m1, other has mass m2, and they are separated by a distance r, then there's a force of gravity between them, and this is given as gm1 m2 over r square, and the force is always attractive, so these bodies attract each other. So this is Newton's law of gravitation. And many years later, Einstein verified the same formula with a different theory, which was called general theory of relativity. Okay, well, we can clearly see here that if we have a massive planet, or let's say Earth itself, let's say there's an Earth with a mass me, and there's a body very close to the surface of the Earth, then we know, and the body has mass m, then we know force of gravity on this small mass m because of Earth is going to be Fg equals gme, and let's say the radius of the Earth is re, gme m over re squared towards the center of the Earth. And if you look closely, this should be rewritten as Fg equals gme over re square m. And you can see these two equations are similar if we define g as gme over re square, where capital G is called gravitational constant. And has a value of 6.673 multiplied by 10 power minus 11 Newton meter square over kilogram square are the units. So you see, again, just to explain, the m1 is the mass of one of the body, m2 is the mass of the other body, r is the distance between them, and g is the gravitational constant. Okay, so this is how g is defined for Earth. We can call it also ge in case you want to use it for Earth. So similarly, every planet has its own gravity. So moon actually will have a different gravity because moon has a different mass. There should be the moon has a different mass, and also moon has a different radius. So moon has actually 1/6 the gravity of Earth. So gravity on moon is less than Earth. Okay. Also, the Earth has this amount of gravity at the surface. Let's say if you are calculating the gravity, let's say this is Earth, not really I haven't really drawn a perfect sphere, assuming this is sphere, and you are at a height edge, let's say some satellite is going around the Earth at a height edge, then this satellite is going to experience a force of gravity given as gme m over re plus h squared. Okay, so here you see gravity has gone down because there's an additional h, where we know that r is the distance between the bodies, and the distance between the bodies is re, where r is the radius of the earth, plus h. Okay, how about if we go inside the earth? So if we go inside the earth, let's say you have the earth, but you dig a hole so that you're somewhere here. And let's call this r itself, and this is re. Then what is the gravity at this point? Let's say you have a ball here. Well, again, it's the same formula, but we need to determine m1 and well m1, where we have to determine the two masses first of all and the distance between them. Clearly, let's say if this is mass m2, and r we already have identified as capital R, so Fg is nothing but gm1 m2 over r square, where m1 we need to find out, m2 is mass of body, and r is distance from center. All right, what is this m1 we are going to use when we are going to use this formula? Well, clearly m1 is the mass of whatever is below the mass, which means we have to take out this part and find the mass of this part of the earth on which the mass on which this m2 is. We are not going to consider mass of this part of the body, I mean this part of the earth, which is outside or above mass m2. It's only the mass which is below m2 in terms of radius, which we are going to consider. So this is the problem here sort of reduces to like that. And the reason it reduces is because of the way this equation behaves, and that we can figure out when we are talking in terms of calculus and higher, and which we can actually learn in higher classes. But right now, the way we can understand this is that this formula, when we are going to use this formula, m1 is nothing but the mass of the sphere that lies below the mass of this guy. Okay, so what is the mass of this guy, this particular area? Well, let's say if mass me is the mass of the whole of the earth, which means let's say the earth is uniform, and we know mass is given as density times volume, and let's say rho e is the density of earth times, and it's a cube, I mean a sphere, so the mass can be written, mass of earth can be written as like that, right? Also, we know the mass m2 can be written as rho e multiplied by 4/3 pi r cube. So you can clearly see you can write m2 as r over re cube times me is the mass of the m2, which is the earth and the dotted part of the earth. And if you put in these formulas inside, then if you put it here, what do we get? We get Fg equals G is G only, M1 is sorry, I used M1 here but labeled them M2 here, so this should be M1 here and M1 here. Sorry for the wrong label. And this M1 is nothing but R over RE cube ME M2 divided by R squared, right? So we have our M1 now, and this reduces to Fg equals G R over Re cube Me M2. As a matter of fact, you can reduce this to G, also rearrange this to GME over Re cube Rm2, right? And this is nothing but gravity, small g, which is for any point inside the earth. So gravity, you see, is changing with R, capital R. As R changes, gravity changes, because R is changing, and this remains constant. G is a constant, Me is a constant, and Re is a constant. So we see here that gravity should actually behave like this. As you start from center of the earth, unless you plot this G, then the gravity should behave like this. In fact, like this, which means gravity increases as R increases, and this keeps on increasing unless you reach R, right? Because as you go and consider bigger circles, the gravity keeps on increasing. So this is what is happening. So we start here, then gravity here, we calculate the gravity here, then we calculate the gravity here, then we calculate the gravity here, and all the time is dependent on R, because we see we are adding more and more mass as we go up, and when we reach here, we get up to this point, R E. Okay, but after that, you see, we already have said gravity reduces, because as you go further up, you do not add any mass below the smaller mass. In fact, it's all space now. So as you go even more further, somewhere here, then there's no mass in here. So gravity, now you know, we already have talked, behaves like Fg equals GME divided by Re plus H square M2. So this is gravity now, as where H is the height above the surface of the earth, and you see it decreases. So it behaves something like this. Decreases, goes to zero, almost zero, as you go higher in the distance. And this is the radius, this is the distance between the center of the earth and your mass M2, as you increase the radius. This is how gravity behaves. This is the line, and this, I don't know what graph is this, but this is proportional to 1 over R squared. In fact, R, you know, is given as Re plus H. Okay, so we will solve some problems to understand what's going on.